Okay, hello everybody, and welcome today for our next webinar series of the OceaniX project. So today we are extremely happy to welcome Christian Lessig, who is a professor at the Ottö-von-Guericke Magdeburg University. Christian is going to talk to us today about representation learning for earth sciences. Thanks again, Christian, for accepting to give this talk today, and please take it off.
Yeah, well, first of all, thank you for the invitation. And I wanted to say, if there are any questions during the talk, then just let me know. Yeah, raise your hand or write it into a chat. Because I think I'm not entirely well calibrated what the background of people here is. So yeah, if you have any questions during the talk, just go ahead.
So just a question, Christian, do you want to, for me to give you the questions throughout your presentation, or just to keep them and then I will ask all the questions at the end?
No, you can bring them up during the talk. If there's something in the talk, especially something where you can follow what I'm talking about, so it's
perfect.
Yeah, just
perfect.
Let's
Thanks.
have a real seminar and not like just
thank you, Chris.
A lecture. Yeah, so I want to talk about representation learning, and earth sciences is like, you should think of it as, I was looking for a general term that is not yeah, that includes a lot of things, because I'm really talking about more or less a methodology that applies to many different domains, and I think that was the broadest term I could think of. Yeah, and the motivation is there are large amounts of data available in the earth sciences. So that's one example is the Era 5 data set. So that's the atmospheric reanalysis from ECMWF. It's about 6 petabyte. A few hundred terabyte being added every month. We have, for example, the very large outputs of control runs for the IPCC and in general for the climate models. That's order hundreds of petabyte that are available at the modeling centers. There's the satellite data, like the new METOP satellite, which generates 864 gigabytes per day per satellite with 8 satellites. So that's also a large amount of data, and to maybe build a little bit of a bridge to the ocean. There are also oceanic reanalyses that also have multiple petabytes of data. And what for me is always very exciting is that this is actually observational or quasi-observational data, because yeah, if you come from scientific machine learning, and that's something I'm also doing, you typically run a large simulation to generate data to train your neural network, and that's a little bit circular. But having actually real data available to train your model, that's interesting, because then the data might actually contain effects we cannot model otherwise, that are, for example, not in our partial differential equations and in what we know and what we model. The question, however, is we have these large amounts of data available. The question is, how can we actually make use of it for machine learning? And there are a few challenges here. First of all, most of this data is actually unlabeled for most purposes. That's, for example, ERA 5, that's essentially just the spatial fields at different time steps over 40 years, and yeah, depending on 10 or 12 different fields. So how do you do machine learning on this data? There are no labels, there's no what you usually use for training. The second challenge is, if you have multiple petabytes of data, you actually you need a supercomputer to do the training and to even store the data and to do anything with this data. So you cannot just like easily work on it with as a, for example, university research group. And a third point, how do we actually make sure our models are physically consistent and plausible? So you really learn something about the physics that also gives us some confidence that it might generalize to different situations. So there might be more challenges, but these are like the big 3 ones that I have on my mind. And here maybe an example of using this large amounts of data is not entirely trivial. So hurricane tracking, that's clearly very important to predict if you have a hurricane, where will it hit land, what will be affected. And it's also actually something important, for example, for climate projections. What will the frequency of hurricanes change? Will their trajectories change? And if you look, for example, at hurricane data, there's like the NOAA Atlantic Hurricane database, that's 6.5 megabytes of training data you have. So that you can maybe train a tiny MLP with like a few hundred parameters on this data. But yeah, on the other hand, you have these 6 petabyte of ERA5 reanalysis. And so the question is, can we somehow leverage these large amounts of data to help us out in these situations where we have only very little specific training data? And why this in principle makes sense, because it's like ERA5 in some sense contains post-processed atmospheric dynamics. And hurricanes are clearly governed also by atmospheric dynamics. So one would hope that if one has a general principle that understands, or a general machine learning model that understands something of atmospheric dynamics, then it would also be able to maybe be useful to be helpful with hurricane data. And the same way as in some sense we have a PDE and we don't, a hurricane is just a specific initial condition if you want for a PDE or mathematical models we usually use. So the idea is also like if you build a general model and now a general neural network model for atmospheric dynamics, then well, we might just have to pick in some sense the right initial condition or adjust a little bit so that it's really useful for hurricane, for example, for hurricane prediction. And there are many different situations where, yeah, we don't have a lot of data. For example, if you do an air pollution prediction, that you have sparse measurements and that's also like typically not much data. Observations with missing data where like you have cloud occlusion or something like this. Classification of extreme events, by definition, extreme events are rare events, so there's always data missing. But then again, it still belongs to the same underlying physical principles. And yeah, this is here really where I think self-supervised representation learning and representation learning in general could be useful. And I want to a little bit make a pitch for that this might be useful for us to be used, and because of this and because it hasn't actually been used very much in the earth sciences and atmospheric science and ocean science, I want a little bit give an introduction first. So that's the next third of the talk will be a little bit in general what is self-supervised representation learning. And then I will talk about how to use it and how to adapt it to the earth sciences and why I think it's actually a very useful tool for us. So maybe first of all, to make the point that representation learning is not a niche in machine learning. So Joshua Bengio and Yann LeCun, these are 2 of the 3 people who won the Turing Award for machine learning or for deep learning for their work on deep learning, to be more specific. So the Turing Award is essentially the Nobel Prize in computer science. And what Bengio said is that humans develop representations and abstractions to enable problem solving and reasoning, and our computers should do the same. So this essentially covers the second part, what is representation learning. Think of it as an abstraction of the input data. And an important point is that it should be essentially for problem solving, so it's a little bit task independent. And the second from Yann LeCun is self-supervised. That's essentially, it's just the title of a blog entry from actually this year. So he said like self-supervised learning, that's the dark matter of intelligence. So and if you dark matter, so that's kind of what underlies everything. 80% of the universe are supposed to consist of dark matter. And so he makes the claim that with self-supervised learning, that's really a basic infrastructure that is just very important to keep everything else working. So what is meant by representation learning? And the idea of representation learning is to have a task-independent representation or abstraction, if you want, of a data in the feature space of a neural network. So one point is that it should be task independent. So you should essentially train a neural network that you can use for multiple purposes. And the second part is this feature space of a neural network. And to make sure we are all on the same page, so here I have an abstract model of a neural network. It doesn't have to be an MLP or specific model. Almost all machine learning models have some kind of stages or layers or blocks that essentially you iterate through, and that's kind of what is the point here. And between each of these blocks, or each of the blocks, is essentially a mapping from some Rn to some Rm. So, and this is one way to think of a neural network as a nonlinear mapping between these different intermediate spaces. And each of these intermediate spaces is essentially just Euclidean space, but the data is always nonlinear transformed between the different spaces. That's the point. And this makes, in some sense, neural networks so powerful. And exactly these intermediate spaces, this is what in the neural network literature is referred to as feature spaces. And the idea is now that how the data is encoded in these spaces is actually something that is useful and that is meaningful. So this is the idea and the tenet, if you want, of representation learning. That here I wrote it now in a bit more abstract notation. So the neural network as a mapping from the input domain to the output domain, and you have these layers in between. And that these layers in between, we actually like, it's meaningful encoding of the data. And the same way as a Fourier transform or a wavelet transform is some meaningful encoding of the data that can be useful depending on what you are interested in. And we know also, for example, Fourier transform, it's some encoding of the data that is actually useful for a lot of different applications. So that's in some sense the same idea. Here, the point is it's a learned representation that is task independent but domain specific. So that's the one part. That's what is the idea of representation learning is. I will give a few examples in a few minutes. I wanted to first cover a little bit the ideas. That's our feature spaces. And the second part is the self-supervised training. And self-supervised training is in some sense, sometimes it's called unsupervised training, but that's that's a bit too much. It is supervised training, but the trick is, if you want, is that the labels you use for your training, this is something that comes from the data itself. So it's something somehow you generate. We will see a few examples. You define the labels based on your data. It's surprisingly simple once you have seen the idea, but might sound a little bit confusing at the beginning. But we look now at examples. But we actually start with the feature spaces. And this is a very old paper. This is 2012 or 2014. I think it came out in 2012. It's a standard convolutional neural network. And what we look here is a visualization of a convolutional neural network trained on image classification. What we look here, these are essentially the feature spaces. So this is the one for layer 1, layer 2, and so on. What you see, layer 1, this is essentially, that's something fairly classical. You have what the network learns, there are essentially edge detection filters in different directions. Level 2 is a little bit hard to interpret, but level 3 essentially is has already a lot of structure. For example, if you look down here, you see that what the network seems to learn is somehow a representation for humans, for photographs of humans. And if you go further down, then, for example, here in this block, it somehow represents cats and dogs that are apparently distinguished based on the shape of the ears. And up here, you have human faces and dog faces and car tires that are all somewhat similar for the neural network. But what we see is in the feature spaces, actually there's structure in there. The network really maps essentially between, for example, here, some low-level abstract feature spaces to some much more concrete ones. And so this is why this idea actually makes sense to think of these intermediate representations of the neural networks as a meaningful encoding that can be useful for applications. And the second task of the self-supervised representation learning is the self-supervised pretext task. So that's the pretext is a common term people use for this. And again, the idea is we don't have labels on our data. So we want to generate labels from our data. And for us, that's important because, for example, the ERA 5 reanalysis, it's a lot of data, but no labels attached to it. And the classical example, for example, for a pretext task is the following. We take an image and we randomly delete some part of the image. Here it's the central square, but it can be just some arbitrary rectangular region from the image. And now we just ask the neural network to fill in the deleted region. And here on the top right, you see an artist drawing. And the point is for the network to actually do a good infill, like here on the bottom right, it, for example, has to understand that there are certain structures in the image. Like, for example, like here, the windows that should continue for a little bit and some repetitive structures. So just by training the neural network on filling in the randomly deleted parts, and all we need for this is some image to be able to do this, the network has to understand some general structures about either general natural images or the class of images we feed to the network. And if you want to train with this task, all you need is just images. So you can download billions of images from the internet and just train your neural network on billions of images. So this is one example. Somewhat similar example that's also fairly old in classical paper is if you have an input image, you can delete the color information, or for example, decide either you give a network only the color information or only its grayscale image, and then have a network actually predict the information you deleted from it. it's also something, if you have a color image, you can always convert it to a grayscale image, and the network then has to learn the missing information. So I hope this self-supervised learning now makes a little bit more sense. So it's actually, if you have data, there's often a way to find out how to delete some part of the data. That's the common idea in a lot of these pretext tasks, and we will see it in a minute as well. And then have a network somehow predict it. And if you do this for large amounts of data, the network has to understand some of the intrinsic structure of the data. And so, yeah, what I showed so far, that's all fairly classical work. And more modern, but yeah, it's already classical as well, although it's just 4 years old. That's the BERT model, and it's for natural language processing. And a lot of people in domain science always think like, why should we care about natural language processing? Because it's like, yeah, we don't have text. We have, our data might look like images, or it's certainly also not images. I think what makes natural language processing always fairly relevant for us is that it's really, we have the same temporal aspect that a lot of the data in, for example, atmospheric or ocean science has here. Because a sentence has a clear one word follows after the other. And yeah, also the standard RNN models, sequential models all come from natural language processing. So, and what we did here in this BERT work is we trained a very large model with billions of parameters. And yeah, if you have this amount of data, there's just no label data set available. So we had to essentially go to self-supervised training. And what we did in the BERT model is the following. We always took 2 sentences. For example, the sun was shining bright. And we did something similar then for the image data. So we essentially deleted one word. So for the image, we deleted one region. Here, we randomly deleted some, or we randomly select a word that is deleted. And then we have a neural network predict the word that was deleted. And we can do this for a second sentence. So she's wearing a gray shirt. We delete the verb here, and the network again predicts the deleted word. And this essentially forces the network multiple things. On the one hand, it forces the network to understand some grammatical structure. We return to this aspect in a little bit. So for example, if you're wearing, you have to have a right ending for the verb and for the verb construction. And clearly the network also has to understand some of the semantics of a sentence to select wearing or wear. What do you do with a shirt? So, and so this is in some sense semantic level structure. And what we also did in this work, they always use 2 sentences because the network was asked to predict if the 2 sentences were actually adjacent in a text. So, right, you can ask this like, the sun was shining bright, she's wearing a gray shirt, if this would belong in the text behind each other. So here, probably not, but that's, and the trick is, this is again something you can just take any book from the internet or any book that has been digitized, and you can train the neural network. So here you have essentially infinite amount of training data. Your only constraint is really probably your compute power. If you work at Google, that's also not so much a constraint. So this is the BERT model. And why would you do with self-supervised training? Well, this is essentially the performance we get on a question answering task. And yeah, sorry, one can't pass the table. I completely agree. But if you just look at the last column, that's essentially the F1 score on the test set. So that's, if you don't know F1 score, it's just a score, the higher the better, the test set. And what you see here, the human performance on this question answering task is 91.2. The best neural networks essentially that were out before we published the work were at 91.7. That's essentially both ensembles. And what we essentially achieved with their, by training on these huge amounts of data we can train on because we don't need labeled data, and we achieve essentially 91.8% accuracy. So what we do is, and that's also a general principle, you train on these large amounts of data so that the network really develops a representation, in this sense, in this case of natural language. And you will actually see in a bit how this representation looks like. And then you do what is called fine tuning. You use a little bit of labeled data, or typically the small amounts of labeled data you have to tune the weights of your big model and adjust it to the specific task. And yeah, BERT was really a model that demonstrated that this works at scale in for natural language processing. This comes out of Google, and this was actually used in production within a year at Google. And a second example from computer vision, that's called Dino, this came out just last year. So this does self-supervised representation learning for computer vision. It uses essentially also one of these transformer models, and I will get back to these also in a little bit. And we did train on ImageNet, but used the unlabeled data from ImageNet. And unfortunately, we do a very interesting training task. It's unsupervised, so we don't have labels. We developed a very interesting strategy with student-teacher training. Unfortunately, it would take us half an hour to explain what we did. It's a bit subtle and complicated, and but yeah, very interesting approach. And what we showed also in their work, so we essentially trained a similar model in a supervised fashion. That's their own previous work, so it's a fairly fair comparison. And so these are different sizes, the small and the big ones. And let's again just look at the last column. So that's ImageNet, that's the classification performance on ImageNet. And so we compare essentially their model just trained on supervised data in ImageNet. So you have labels, you can just do supervised training, where we achieve, for example, this model 79.9% accuracy. But if we actually first do the self-supervised training and we force the model to develop good internal representations, we ultimately achieve a better performance. And here we actually would have had the chance to train on that much larger amounts of data, which we didn't use. So that's something that would be interesting to see how the model would perform if it was trained on even larger amounts of data than just ImageNet itself. But even if you take the same amount of data, you actually can achieve better accuracy and better models by doing self-supervised training. This has to do by, if you choose the right pretext task, you really force the network to develop good internal representations, and this makes it then easier or easy to answer specific tasks you want to get to. Good. So the last two works, we were not, yeah, these are the classical, these are pretty well-cited examples of self-supervised representation learning, but we also both share one more commonality, that's our transformer neural networks. That's also something I want to advertise a little bit in this talk, because I think that's also something that is very useful. It's an absolute standard model in the machine learning literature these days. And there are two reasons for this. The one reason is that we scale very well for parallel training. And if you have very large models, that's one of the things that works substantially better than, for example, convolutional neural network. These are numbers from with papers called vision transformers. What we only care about is essentially the last row here, which is the compute time. So that's the tensor processing units from Google and how many core days we use, so huge amounts of training time. But what you see with a transformer, and that's a very large transformer model, the H stands for huge here. So you need 2.5K core days. The point is that this is a quarter of what you need for a standard convolutional neural network, a ResNet model with the same number of parameters. So the point is these transformer models are easier to train, and this was essentially the first selling point. They are easy to parallelize, and you can train them faster because in some sense they map better onto the standard GPUs used for training. And the second point, and that's something I find ultimately more interesting, is they are based on something called an attention mechanism that allows you to model complex dependencies in your data. And you typically do this through some learned inner product and feature space. And the point is here that these have lags in the input domain. And this allows you to directly interpret the learned representations. So we saw before the BERT model and the Dino model that use these transformers, and they are very efficient, and we have a built-in mechanism to understand what we do. And the difference here is, so there are various ways for introspection of neural networks, but we typically use some kind of nonlinear optimization to understand what is going on. This attention mechanism is something you directly take what is used in the neural network and you just visualize it, and it has a very good interpretation and meaning. Let's look at what I mean. We go back to the BERT model. So this was this natural language processing model where we trained on predicting two sentences or the deleted words from two sentences. And we essentially look at this attention. Attention essentially relates. Attention is that, in a technical term for it would be a correlation matrix or a correlation between different tokens. And the nice thing is, independent of how deep you are in your neural network, you can always directly relate it to the input. And the example we will use is this very intuitive sentence here. The law will never be perfect, but its application should be just. This is what we are missing, in my opinion. So it's a fairly complex sentence. And so let's look at what the neural network, how it correlates with different words in the sentence and with the attention. And it actually has multiple layers. So the attention here, there's one attention layer where you have very low level grammatical structure. For example, noun, the article, sorry. Here you have a low level verb construction, will never be perfect, its application, and so on. So the network really understands like the basic, very fundamental grammatical building blocks. It learned it out of the data we didn't specifically tell the network to learn the structure, right? We always taught it to learn the word we had deleted, but it figured out that's a good way. If I have to solve this task, I actually have to understand this, or that's a good way to at least solve this task. And the second part, or that's the second attention layer here. What you see here you have actually larger grammatical structures. So these essentially, you should think of them, we exist in parallel. So this exists in this, and we are both combined in some way. And here you see the law will never be perfect. For example, that's essentially, right, that's a perfect, that's a sub-sentence. So, and the network really understands or learns that it has to correlate with data on these two levels to answer this task. So I will explain at the end a little bit more detail about how this works, but it's directly out of available from the network, this correlation information. And we can look at it for how it looks like for images or for this computer vision task. And the point is it's always available in the input domain. So if you go on computer vision, you have it available as an image. And we can, for example, pick this image of a zebra-like object. And here you see that what the network learned, or it wasn't told to learn it. It was trained on some quasi-classification task. The network learned automatically that image segmentation is the right thing to do to solve a task. So, and here's a second example where you have a road and it's segmented in the road, in the bush here, in the rail guards. And this is essentially the network. If you do representation learning right, the network learns the internal structure of the data, like the low-level grammatical structure you have in sentences, or here that an image really consists of different objects, and it helps to segment them if you are supposed to answer tasks on the data. So, and yeah, this is essentially a little bit the essence of self-supervised representation learning, and specifically with these transformer architectures. So, how can we use this for earth sciences? And I want to give essentially two examples. One is on a distance function that really uses these feature spaces. And then I want to return to these transformer architectures and the attention maps. And again, the situation why I think representation learning makes sense, because we do have this large amounts of data, but it's essentially unlabeled data. And for a lot of, so we could essentially we can come up with these pretext tasks or with self-supervised learning tasks, and I will give essentially two examples what one can do. And then we can use actually train neural networks, like for example, understand atmospheric dynamics or understand ocean dynamics. And then we can do this fine-tuning using the small amounts of labeled data that are available. So, and one project we did in this direction is AtmoDist. And the starting point is, if you want to train a neural network, you need a good distance function. That's right, that's the loss function you have in your neural networks. And the ones we have from mathematics, like L2 numbers, are not actually typically very good. And to have an example of that we are not very good, so that's vorticity, directly from the era 5 data. And now what I plot is essentially the distance to the initial time step. So, and you see the atmosphere is moving, and correspondingly we can compute the L2 distance, and that's what we do here, or the mean squared error. And you see there's actually this kind of proportional to the time. That's what you want to have. You want to have that the error grows proportional to time, because this is something that would be useful and necessary for most learning tasks. The issue is now that about after like 1.5 days, the error actually plateaus. So here we, for example, have this large coherent Lagrangian structure that travels, and as a human, we could easily tell that the distance is increasing because this Lagrangian structure is traveling. And we could, in some sense, based on the distance of a Lagrangian structure, tell the time that has passed. But the neural net, essentially, if you take the L2 loss at some point it just plateaus after 1.5, 2 days, and it can't tell you any difference any longer. And that's suboptimal. And the idea is essentially to come up with a custom distance function. And how do we do this? Well, we return exactly to these feature spaces we have here in the neural network. And what we do is, so, right, these are our feature spaces that come out, that essentially rise through as the intermediate data that arises in the neural network. And these feature spaces are task or domain specific, right? So we encode really your data, and the idea is now to compute the distance in these feature spaces. And it's nothing we invented per se, so that has been used a lot in computer vision already based on pre-trained networks, but it hasn't actually been used in the, let's call it earth sciences. And here we use the ERA 5 data set just because it's a large amount of data, it's close to observations, but yeah, well, it's also unlabeled, right? So we do actually have to come up with a pretext task or with a self-supervised training task. And the one we developed for this work is the following. So if you take the ERA 5 data, it's kind of time slices every 3 or 6 hours, depending on what you do precisely. And each of these time slices represents some atmospheric state. Plot here again the vorticity. And yeah, as is common in computer vision, we typically look at some local patch, although it's not necessarily essential for the work. And what we essentially, the task we came up with, if you take 2 different slices, say like today at noon and today at 6 p.m., right? These are 2 different atmospheric states, but they are clearly related. You can see here this Lagrangian structure moved here, and here there's also some movement there. And the task we gave the neural network is, if we clearly know the distance, right? That's where we indexed our array. But if we just give a neural network just these 2 slices, we can ask a neural network, well, what is actually the time difference between these 2 slices? This also has some theoretical justification if you think of the ideal models or the mathematical models of ideal fluids when it's a geodesic flow, and then this time difference is really an intrinsic distance for the fluids. But you can also just think of it as a heuristic pretext task. And this is exactly what we did. So what we do is we take 2 slices and we kind of hide the delta t. That's only something we know, but not the neural network. We feed these 2 slices into a neural network. It's called a Siamese neural network. It just means it's one neural network and you feed 2 inputs to it. What we get out is 2 internal representations, right? Here at the end, we do have a feature space of a neural network. And then we put it to a small classification network that uses this internal representation. And this network is by construction small, so that we really learn good representations. And then we predict the delta t. And the point we are interested in is really this internal representation, right? And then what we want to use, so we train the task on predicting with delta t, but that's really, we don't really care on this prediction. We hope we perform reasonably well because it tells us that you learned something. But what we care about, that here this embedding in the intrinsic space is actually good. And so that we can compute a distance in this embedding space that is more meaningful than the L2 distance between just the spatial patches of vorticity, where we know that's really not very good because, for example, it has no idea about Lagrangian structures. Good. So, and that's really the distance function we then define. So we have an embedding of our vorticity field zeta, and that's the distance we use. And we trained this on ERA 5 reanalysis. Since we don't, I will go a little bit faster. We just use standard ERA 5 reanalysis on one vertical layer. And we fed it to a standard, that's a standard ResNet network, very standard convolutional network, very standard 2.2 million parameters. We feed in vorticity and divergence actually at time t and some time later. And then we predict the temporal distance, which we hide from a network. And as I said, what we are interested in is really the output of a network, or the encoding of a network at the last block, because we can take the weights, and this is just a vector in Rn, and compute the distance based on these weights. And what we see here, that's essentially comparison. We can take two slices, vorticity at time t and vorticity and divergence at time t and vorticity divergence at time t+1. And we can now compute this distance, gives us some number, and we can compare this to L2 distance that I showed at the beginning. What you see here, the blue is the L2 distance, and the red one, or orange one, that's our distance. And the first thing we see, so first, our distance, that's a little bit more linear at the beginning, and that's kind of what you want to have, that the distance between the patches should be somewhat linear compared to the time it goes out. And we also see that it has a far smaller variance. So the MSE error, the L2 error, kind of, it oscillates a lot depending on which particular patch you pick. You can be lucky, you can be very unlucky. Yes, our distance is much more consistent, and it's typically what is much very useful for applications. So, and what we did since, right, so we defined a new distance function, and what you can do with it, you can train a neural network. And that's also one of the standard things you have in representation learning, right? You want to solve a second problem almost in the end. The second problem we picked here, that's downscaling, or upsampling or super resolution, depending on where you come from. And we did this with the Garn of Stengel. So this was published in 2020 in Proceedings of the National Academy. So fairly well published paper, and we thought that's a good baseline. And what we did there, we essentially replaced just the mean squared error in their paper. So we trained a neural network with mean squared error, and we replaced this mean squared error with our learned loss function. And we did 4 times super resolution in this work. And what you get with this, so this is comparison, this is the Stengel work on the right, the ground truth in the middle, and ours on the left. And I'm not sure if this is good to see on Zoom, how strongly they compress the image, but I will upload the slides and you can look at it afterwards. So what you see, what you certainly should see here, that on the, and I think it's too much compressed, that here you have more detail in our work than you have in the Stengel work that is trained with the L2 mean squared error. And similarly, here, a different example where here things are much more washed out. And that's a standard artifact you get with mean squared error than compared to a ground truth in our work. And with the second field, here you again see that this here is more washed out, and here actually you should see that you have a little bit more detail. So that's eyeball metrics, always a bit subjective. So let's look at something more objective. That's the energy spectrum you get for the data. And the blue line, that's the energy spectrum in ERA5, which we take as ground truth. Although that's an artifact. It's essentially also something that comes out of ECMWF. In any case, if you train with mean squared error, you see that you get a little bit too less energy, fairly consistent across all bands. Whereas if you train with our loss function, with our representation learning-based loss function, that's the orange line, you do get consistently a much energy spectrum that is pretty close to a ground truth. That's a semi-variogram, so this measures the local correlation. And here you also see that we get consistently better with our work than with the mean squared error. It's even clearer in some sense with the energy spectrum. Good, I will skip this part. So this shows that we also perform well on the local statistics, or we didn't train on it, so that's good. And so the point of this work is computing the distance function in the embedding space that we learn through representation learning does improve applications, and we came up with this specific task to do the representation learning with pretext tasks, that we have a neural network predict the distance between 2 atmospheric states. And that's something we can do on the ERA5 data despite having labels. And we will present some new results on this work next week at EGU. So if someone is around or joins online, it's Tuesday at 10:26 sharp, I assume. All right. Good. So, and now I want to go a little bit back to this transformers and to attention mechanism. So we saw this attention mask before. This is left for the natural language processing and right for computer vision. And the question I was asking is, what happens if we now take essentially data that we are interested in, like spatial time fields. So, and I did first, we will get to atmospheric vorticity back in a few minutes, but I will first do with what the first experiment was with a simple channel flow. So you have an inflow on the left, you have an obstacle, and behind the obstacle, you get a von Karman street. Sorry, the visualization is not super great, but I think you all know the principle, and you have this oscillating von Karman street behind. And what I used was vorticity. So that's a divergence-free flow. So I used vorticity because it's a scalar function. I can just use essentially something similar to the things, the networks people use in computer vision. And here you again see this von Karman Street. And we do again representation learning, and we use a transformer in this case because we want to look at attention maps. The representation learning task, oh yeah, and there's some variability in the data because we trained the obstacle was actually at different positions. So, and the specific task we trained on was we give the network a local patch or 3 local patches from t-2, t-1, and t from the past, so 3 time steps essentially, and we have it predict a small region in the future, so at t+1. So this was the task. The network is supposed to get information from these 2 three time steps and a spatial neighborhood around the target, and it's supposed to predict the values in this region. It's an 8x8 neighborhood in pixel space. And yeah, the network does pretty well on the prediction, but it's also very simple channel flow, so you would hope so. But this was really not what I was interested in. I was interested in attention maps. And this is again the input the network got, and these are now the attention maps. So this is the same as the image segmentation you saw before in computer vision. And now the question is, what can we actually learn from this? So what we do see is the flow structures kind of is also represented in these attention maps. So in some sense, it also seems to do some kind of segmentation. So that's there. But let's look a little bit closer of what this actually means with high attention value. So blue is low and this yellowish is high. And again, remember that we try to solve this prediction task. And what essentially this high value means is that this is something, a region information from where that's important to do this prediction task. So, and this is not somehow in a intuitive sense important, but it's actually mathematically precisely important, because the values of these attention maps, these arrays here, these are these Aij values. And what is used for the prediction, these are the Pj values. And this here is something, as somebody who comes from scientific computing, I really like this formula because that's standard basis representation. So you take these attention weights, and if you have a high weight, you assign a high weight to the Vj vectors. And you can think of it as normalized vectors that you somehow sum together to get out a new vector in Rn. And this is what you use for the prediction. So this is in a very precise sense, high values of Aij actually really contribute a lot to the information that is used for prediction. So there's here the sigma. What is the sigma? The sigma is the softmax function. So in some sense, it filters the signal. And this is what happens if you do softmax. It's in some sense a smoothed argmax. So it picks out the values that are really high and sets everything else to 0. So we see what is really used for prediction is this region here. And if you look down here, it's essentially the frontier it seems to use to do the prediction here. And if you look at the other attention maps, so these are the attention maps from the past, it really seems to track here with physical front and use this to do a prediction here. And that's something I find that's from a physical point of view kind of plausible. That's also something I would do with myself. I would look how the front is moving through time and would use this information to do a prediction. So, and in this sense, we can say, well, the network might have really learned something about the structure of the physics that is useful to doing the prediction. And correspondingly, all these blue regions is something that decided are irrelevant, or at least it doesn't need it to do the predictions. We can look at some more of these attention maps. So here we have, that's the obstacle we see, right? You clearly have here the high vorticity values at the front of the obstacle from where the inflow is coming. And you also see this very clearly in attention maps. And the network also knows that really the boundary layer, that's really where like all the interesting stuff comes from in the flow of around the obstacle. It really should focus on where the boundary is of the object. And here a third example where you clearly have, where you again have a nice clear front moving through space. You again see it very clearly in the attention maps. And yeah, you again see that the network focuses here essentially on this front, and it's tracking this, how this front is propagating through space. So this was essentially this nice ideal channel flow. And let's look at atmospheric vorticity. So that's all, it's the same setup. We have 3 time steps. and we again look at a small neighborhood, and we again essentially do this prediction of the value at time t+1. And so this is a nice wavefront moving through the atmosphere, but that's reanalysis data. So that's more or less real data. And here you again see in the attention maps, you can essentially have the wavefront you have in the data is fairly nicely represented. Although it's all a little bit more messy. And this has to do with, the data is just a much more complex system with much more effects. And also, if you look at the thresholded or with the softmax attention maps, it doesn't look any longer as nice. And what you also have in the atmosphere are much more complex, much more messy states, and where you also see that the attention maps are not that nice and not that structured any longer. And that's essentially what I'm currently working on to get nice attention maps also in these situations. And here there's a point I want to make, maybe also why I showed these attention maps. In the past, we often use scientific machine learning. What we often try to do, we try to constrain our machine learning models with what we know about the physics about and from our mathematical models. We say our machine learning model should be energy conserving, it should have certain symmetries. And I think, at least if you have observational data, what I'm personally interested in this observational data is exactly what doesn't fit neatly my mathematical models. What doesn't essentially, like, for example, the atmosphere, you have a big issue that you don't have a closure model. We have things going down to all fine, very fine scales. And so I think what would be really interesting for physical machine learning is to really avoid all these inductive biases, all these mathematical tools with PDEs we are used to model our physics, but it's also, we model these things we can model well with PDEs, and to really train our neural networks on modeling these effects maybe that we cannot represent very well with our classical mathematical tools, and to really essentially like use the possibilities these models give us. And I think here really these attention maps are actually something very interesting because they allow us to ensure the physical validity of our learned models in an a posteriori sense. We can look at it. And I do think also that it might actually be something interesting to understand physical systems, because here, if you, right, we looked at this here, it tracks the wavefront. And if you think of a complex phenomenon, like for example, ENSO, and you would try to learn this over very long time scales, maybe these attention maps actually tell you some interesting things about causal structures and correlation structures about things where our current models are not very good, and they are not very good also because the PDEs are infinitesimal in space and time, and with a long-range spatial-temporal relationships. So here I want to maybe provoke a little bit and think maybe we should think of a machine learning as a complementary tool to the tools we already have. Good, and this is something we currently try to scale up a little bit with Ilaria and Maike, Martin, and Anish to really do a representation learning on a large chunk of ERA5 reanalysis, so 500 terabyte, to really get a representation of atmospheric data that can be used for a variety of applications and also to do get scientific insight. And the idea is really to use a supercomputer to train once on these large amounts of data and then provide the model to the community so that we can use it, so that everybody can use it. And now I'm almost at the end. Small advertisement break. We do a workshop on transformers in the earth sciences together with Martin Schulz mainly in September in Magdeburg. And the idea is to get really machine learning experts together. So we have hopefully some people from Google and DeepMind, and also then domain experts who are interested in machine learning and maybe have a little bit of background, and to really try to find a little bit of synergies between the two communities. The website will be up next week, so if you're interested, check just my homepage next week, and there should be more information. And with this, I'm sorry, I'm a bit late. I'm getting to the end. So I do think self-supervised representation learning has great potential and untapped potential for our domain, because we have large amounts of unlabeled data we can train on for representation learning, and we have often very little labeled data, and it's also very hard to actually get labeled data, like mechanical Turk or anything like this won't work for us. So, and I do think, and that's maybe a hypothesis I put out there, that representation learning also has the potential really to help us to understand physics and, for example, finite time or finite spatial temporal interactions in systems. Thank you.
Thanks very much, Christian.